Alright, cool. And that's a wrap. Alrighty. So today is Monday, so chapter 4, problem 8. Alright, chapter 4, problem 8, first common ancestors. CTCI. Chapter, we're trying to make them a little bit better. Problem 08. First common ancestors. Okay. And we will just copy most of this. We probably don't need all of this at all. Oh, you know what? We had a template thing actually. Let's copy that. And could not resolve simple input. Okay. Yeah, our template should be valid from the beginning, so that's kind of not great. But let's actually change our template a little bit. Alright, so chapter 4, problem 8. First common ancestor. Design an algorithm and write code to find the first common ancestor of two nodes in a binary tree. Avoid storing additional nodes in a data structure. Note this is not necessarily a binary search tree. So it's a binary tree, not necessarily a binary search tree. You're looking for the common ancestor, which is very similar to the one we did in chapter 3, I believe, or chapter 2 on linked list. That is just like find the point at which two lists intersect, and avoid storing additional nodes in a data structure. I wasn't planning on it, but seems like we can do basically the same thing, right, as we did in the linked list. We should. I mean, what was the algorithm to find the common ancestor in the linked list? It was pretty easy, actually. It was take the length of the two lists, right? Whichever list is longer, drop items off the longer list from the head of the list, obviously, until the two lists are equal, right? And then start processing the list concurrently, dropping them concurrent items off the head concurrently until you have the case that the two nodes are the same node. If that does occur, you found the merge node. So let's see if that could work on this. The common ancestor of two nodes in a binary tree. So it's basically, looked at the point of view of a node in a binary tree. The list, quote, in this case, is the path from that current node to the root node, right? And I think we do, once we have the path, we have a linked list. And so we basically map this problem onto that problem. And I think that's just the solution, right? So, yeah, that seems reasonable-ish to me. Okay. Alrighty. So the name of the function is find common ancestor. The thing is takes a node, or really a node, the root, a tree. It's all the same thing, right? But it takes a node. That's the most generic thing we can say, and This is what we expect it to be. This is function, and this is the takes the node, right? And I think maybe we can sit with our, what did we do last time? Chapter 4, successor, right? We basically just defined our nodes as these sort of things, which I think was modestly successful, you know? Kind of, all right. So, wait a minute, maybe I'm backwards about what this says. What is this saying? You're given a design an algorithm and write code to find the first common ancestor of two nodes in a binary tree. You know, they keep saying stuff like this, but okay, so I think we have to do the same thing again, right? Where it's kind of like we're going to have test-wise, what data do we need? We need the tree itself, right? We need node 1, and we need node 2 value, really, right? And then we need to see what we expect. I don't know why it's doing this giant thing there. Right, and we've kind of done this before with this over here. It kind of sucks to have to write this every single time, but I don't know how else to write generic tests for this. Could I write this without having seen it? Take the lock, you iterate up next, you take while inclusive, that you're not on the end. Oh, it's I don't think you need this for this one, because if you did start at the root, right? If you start at the root, you are going to get the end as the first node. And so you can just drop the last one. But that does require you putting yourself as the root. Okay. Then you just do this very obvious thing. Then you take the first one. On the assumption that there's only one node in your binary search tree that has that value. Or sorry, in your binary tree. This is not necessarily a binary search tree. Okay, so I mean, although we could, I think I'm just going to copy it. And I'm actually going to take this one out and just say, hey, look. I know you passed me a lock, but we're just going to start you from the root. It doesn't really matter, you know? Unfortunately, zip/root does, I believe, return you a node and not a lock. Yeah. So that's okay, but that just means we need to basically take the lock again, or we need to create the zipper again for it. I guess that's why we did it ultimately. Well, I guess because this is such a common pattern, let's actually take the while inclusive. And let's think about the thing that converts a node into a lock. I wasn't crazy about it last time, honestly, you know. The way this looks, it can be kind of hard to read, you know. I mean, I don't think it could be expressed much more succinctly than this. Well, the nil thing we could do without that, honestly. Okay, I'm alright with this. At least it's like pretty basic. Let's stick with it, you know? Do we want to do the nil thing? Is there something that I kind of don't like having to do the nils? That kind of bothers me. I'd prefer to not have to list the nils when you don't have anything there. Rest. Well, what if we did the rest, then we filter out or we remove nils, right? And then we count and we ask, is that positive? So now we're saying you can, I mean, if you have to put the nil in there because you have a right but you don't have a left, that's fine. I just kind of just don't like that period. And if we're going to do that, to get the children, you do need to take the rest. That's fine, I think. If you just needed the left child, you have only put the left child in there. If you need the left child, and if you did not need the left child, but you did need the right child, you put the left child in there, but not the right child. And if you needed both the left child and the right child, you'll put the left and the right child as both on nil. So either way, rest works. Similarly, rest works here. They remove the nils. We count the number of items and we say positive. So it's actually equivalent to say is actually equal to x. I don't. X nil and is also equal to just x. Right, is what we're sort of implying here. Now, unfortunately, it's going to always build the thing with nils, but I'm going to undo that and say I'm just going to go through all three permutations basically because it's silly otherwise. Alrighty. Okay. Yeah, I guess this makes sense. I don't know. Something feels. I guess with this many arguments, I kind of feel like we actually should do that little weird thing we do where it's like. Well, this can't happen. I mean, yeah, if you're the same node, you should definitely. Could not resolve symbol zipper. Okay, yeah, that's true. Could not resolve symbol remove. Where's remove? Line 12. Yeah. And I don't need to remove nil, I need to remove nil. Node. I see that right here. 132. Oh, line 32. We're probably going to do something like we've done before. We say node to lock. Actually, I guess so. Right? I mean, And then, yeah, I guess. Oops, I meant, I did that wrong. I thought I was editing the bottom function. Alright, okay, so we still return nil. Find common ancestor takes two nodes. One node, let's just say root, since, or I guess at least root node. Find node with value, v1. Find node with value, v2. Okay, so that should get us set up correctly. So we're passing in two locks to this guy that are both put at the position that they're currently at. If we didn't do it that way, what we'd have to do, if we were literally handed two nodes, right, and then I guess a third node, which is the root, right? I mean, that's the only way it's a tree, so that's the only way you could possibly. So I think that their version of the function would have to take three arguments. The root node, the first node that you're searching from, and the second node that you're searching from, right? Because and then you'd have to find the path to your first node. You'd also have to find the path to your second node, and then we're basically doing the same thing, but we're just going to use the zippers to build a path, basically, or to just the fact that zippers have the path within them to do that. So, on this assumption, what should the path from one? I guess the intersecting thing would actually be the exact thing, right? The identity, right? Right. Okay. So that should actually say, well, they are the same node, you know. And let's think about that. Okay, and so given that that's true, what we want to do is we want to basically say each of these have a length, right? Oops, I mean like this, right? And the length is let's just be dumb about it and say, oh, we'll be smart about it. And it's not really the count of a lot, but whoops. So all we're gonna do is literally say take the lock, get the path on the lock, and get the count on that path, right? And I don't know if the path includes your own node or not. Let's see. Returns a sequence of nodes leading to this lock. So the fact that it looks at p nodes makes me think it's looking at the previous nodes, right? And so I think that actually is not including you. So I think for both of these guys, it would actually end up being empty, right? For this particular test case, because both of these guys should be. Let's actually just confirm that we are getting lock 1 and lock 2 like we think. So I'm gonna just comment this out. Let's just say, am I getting lock 1 and lock 2? Let's make it slightly distinguishing. 2. Yeah, lock 1 is this, and lock 2 is this. So good. It looks like we actually are getting the data correctly, right? Okay. We're getting the data into the lock form correctly. So given that we've done that, let's ask questions like, okay, what is C1 and C2? I think it should be 0 for both of them. Resolve percent. And we get 0 and 0. That makes sense, right? And then, okay. So when we're I mean, this is kind of one of those like identity versus value things. I'm not 100% clear that they're the same thing. Oh, you know, we forgot to actually do this part up here. But let's... I'm going to assume that every node has a unique value, right? And so I'm going to do value comparisons and not identity comparisons. I'm going to say if the first of well, I guess let's say if the map of the this zip slash node, right, first right, if both of these guys are equal, they could also be equal if they're both nil, so that makes sense. Should that ever happen? I don't think so. But if both of these guys are equal, right, then we've found the common ancestor, and we should return just either of them, really. Yeah, so I think we return zip slash node of well, it doesn't matter, either one, right? They're now equal. Right? But if we haven't, then we should probably go up, and we should pop one off the block one. Wait, this is I'm actually skipping. Well, this is what we haven't yet done is actually equalize them, right? So one is going to be bigger than the other after this, right? I think this is what we're ultimately going to do when we actually have equalized them, but we do need to make them the same length. And so let's just go through all the possibilities. If C1 is equal to C2, then we can just keep looping. I think we can maybe do some sort of loop recur thing, right? If C1 is less than C2, then we need to subtract from C2. We need to subtract C1, right? And then we need to I feel like repeat or iterate or something like that had a number argument we could do. Not iterate, but maybe somebody like him. That wasn't it. Okay. Anyway, iterate zip slash up on If lock 1 is less than lock 2, we need to be dropping lock 2, right? Okay, we're going to take how many? We're going to take C2 minus C1 of them, right? Or we're going to drop C2 minus C1 actually of them. Well, we're going to take, and then from that we're going to take the first, I believe. So zip up. Well, the first one will return this lock 2 just unmodified, and then the second one will be with 1 drop, right? So I kind of feel like we actually maybe need to take -1 or something. If they're the same length, what would happen? If they were the same length, that'd be 0. You take 0, and you take the first one having... I mean, taking doesn't really... Yeah, we do definitely need to be dropping. Right, so... Okay, now if there's a... If C2 minus... If C1 is less than C2, we have a delta. We're going to drop the delta. But the first item in here is actually the original lock, right? So we actually kind of want the rest, right? We want to start from having done up 1, you know? Oh, no we don't. No we don't. I'm just getting confused. Right, because the first item is going to be... If this was 0, if this evaluated as 0, then that would mean you wouldn't want to drop any. So you want the first item, and you just take the first item. But if this is 3 and 2, right, you're going to want to drop 1. That's going to drop the first lock, which is the unmodified one, and give you the lock with zipped up 1. And that does seem right. Okay. Just reverse this, and change this to that. Otherwise, if C2 is less than C1, we want to subtract C2 from C1, and we want to drop from C1 the bigger one, the longer one, the deeper one, right? We want to drop from that one. Otherwise, if C1 and C2 are the same, we're just going to loop on something like this, right? But rather than do that, let's actually just return. Let's just return stuff. So this gives lock 1 and lock 2, this one gives lock 1 and lock 2, and this one just gives, quite simply, lock 1 and lock 2. Right? So now, at this point, we have lock 1 and lock 2 are definitely equal sized, you know? And so we should be able to pass that to something else that's going to ensure that these two guys are equal. Let's talk about what we pass it to, which, for lack of a better name, I'll just call it prime. Right? And it's going to pass in two arguments to this guy, and we're just going to be like prime. Same signature, same whole thing. It's just that now you're effectively guaranteeing that lock 1 and lock 2 are the same size. And let's just confirm that by saying let's just say this right here. Right, so now what it actually ends up returning will be 0 and 0. They shouldn't be size 0. Oh, the path, yeah, it should be size 0. And so if they're the same size, and actually let's put that in the precondition. That's not a terrible thing to be just confirming. Does the precondition come after the function argument? Pre and post have sort of fallen out of favor, I feel. Closure. Yeah, kind of makes sense that it should come after. Let's just confirm that that's true, right? Cool. And then, now we don't have to keep checking that. We can just assume lock 1 and lock 2 are equivalently length. They're at equivalent depths, right? And now that we know that that's true, we can just sit there and do a kind of a goofy loop recur with lock 1 and lock 2. 1 and lock 2. Right, and that can just be this. Right, so lock 1 and lock 2, we're just going to walk by them directly, and we're going to say if the two guys are equal, right, then return either of them, right? But if they're not equal, recur. You know, I very rarely do this, but I'm pretty sure that we don't even need the loop here, because if the body of the loop is identical to the actual function signature, I don't think you need to do this. Yeah, so we're basically saying, yeah, if you're equal, then cool. Otherwise, if you're not equal, just recur up. And we're going to keep doing this as long as you're not nil. Of course, this precondition will now fail on nil. And that is the case when they're, well, it doesn't really say. I mean, everybody has to have, every two nodes from a tree ultimately have to have some common ancestor, right? If they're from the same tree, they have to have a common ancestor. And so I don't know if we need to check for the fact that zip/up will eventually return nil. I know, I still don't get why up, down, left, right all can eventually return nil, but next does not. That just still bothers me, but yeah, I kind of feel like this is it, right? I mean, you go, you take the link that you figure out their depths, right? Then you say, okay, let's trim off the bigger guy to make him equivalent in size to the smaller guy, you know. And so you've guaranteed that. Then you just recall the function. And you're basically just going to call a function that's going to two nodes at a time, or basically lock at a time, 2 locks at a time. Just keep going up until it finds a node where you do match, and at that point, you're the common node basically. So let's see what happens. It seems to have worked for this one. So let's get some more intelligent testing here. It's also, one thing we didn't do is we never actually fixed this, did we? Okay, so rest remove nil. Oh, this is see, this is the thing that asks, is this a branch? So we're saying rest, we're going to remove all the nils, and we're going to count and ask if it's positive. I think that is a correct branch. The rest simply returns the current children of the node. This guy, I think the easiest way to express him is probably just like there's 3 possibilities here, right? You can either be Actually, I guess there's only two, really. Oh, I don't really know. So, if you're nil y, then you definitely need at least two arguments. Well, no, sorry. I'm just going to do all three possibilities. There's three possibilities total. Either you're nil y and nil z, right? In which case, we're going to basically return at v, right? Or you're y and nil z, right? In which case we're going to return the ugly one at v nil z, right? D. Is there like a drop end? Let's see. Take last. There's a take last. Oh, but that's just for a fixed. Drop last. Oh, there's a drop last. Oh, that's different than what I thought it did. I thought it dropped everything but the last items in the collection. Why does this return 2, 3, 1, 2, 3? Actually, it's interesting that it returns 1, 2, 3, all but the last in default 1 items in collection. Huh. So we have take while, we have drop while. Those are fine. But what does take last do? Take last 2 items. I feel like there's one in here that I'm missing, but whatever. Alright, so anyway, let's just do it this way. You got y and z, then cool. Just do byz. So you're either 1 or 3 arguments, basically. Oh, wait, there should be a 2. Yeah, okay. Either 1, 2, or 3 arguments. But there should also be... No, it's really just if you're z, right? If you are z, then you should return v, y, and z. Y may be nil, y may not be nil. But that's how you get 3 arguments. If you're just a y, but you're no z, then return just vy. If you're just a y, if you're neither y nor z, then return v. Is this in the best order? I think actually this is the most permissive, because this accepts 2 things, y and z, right? This one is the strictest, right? Nil z. And so I think it may be the case also that now that we've put that one first, but we don't yet know that Does that make sense? I don't know. It looks ugly as hell to me, too. I just don't like it. Let's put them in order. If you have a Y but you don't have a Z, do this. Else, do the whole thing. If you don't have a Y and you don't have a Z, then do the V. If you do have a Y but you don't have a Z, then do VY. If you have anything else, do VYZ. And I think that makes some sense. I think that should leave things, as long as you start them in this form, right, where you don't put in extraneous, you don't put in trailing nils. As long as you start it in this form, it should keep them in this form. It shouldn't change the structure, the look, the values of the trees. Those of the trees should be being compared by their first argument, not by their total structure. Okay. And I'm, as you can see here, going to literally ignore anything past 2 arguments on children, because it's a binary tree. I guess that all makes sense. Okay, so big surprise, we're passing when we do the same thing twice, but what if I do, so now this should be a valid form. Yeah, what if I do this? Fudge. Cannot call with 1 argument. What does that mean? First. That means we're trimming, right? So let's actually first just comment this guy out so that we don't need to worry about something happening here. I should just comment this out. So cool, we're still failing here. So we definitely know that it's actually one of these. So yeah, we got the first, we got a lazy sequence we're filtering on. I don't know why we're filtering here, but we're taking first, the zip next. Why is that occurring? Branch. Okay, zip. Zip up is definitely, should be called with 1 argument, I believe. Well, let's just sanity check this by print lining C1 and C2. 0, 0. Ooh, that's not good. That should be 0 and 1. Huh? I'm missing something? What's going on? Why is this not even calling once? I feel like, oh, so you're telling me you're not even calling into this at all. Oh, zip next right here. Okay, you got a lock. You're calling zip next on it. Okay. Find node with value 2. Okay. You're trying to call branch is what you're trying to do. But it looks like that's not working. You're calling rest. You're removing from rest all the nils. You're counting it and you're saying is it positive? Yep. Both count and positives definitely take one argument. Remove the nils. That should be okay. Okay, I just want to make sure that you're still alive and active. Taking the rest, removing the nil. Alright, well, this is why we need to bring this guy. You're not even calling into this, you're saying. Where the heck are you going wrong? You gotta be going wrong somewhere. Where are you going wrong? Alright. Root node lock, find node with value v1. Okay, how about you just show me this? Okay, that works. So that's v1. Okay, that's actually the problem, alright. Okay, we're still okay here. Okay. Find node with value v2. Cannot find. Iterate zip next. Filter zip / node first is equal to value. I don't really see what's going wrong here. Seems okay there. How about here? Seems okay there. Does it? Well, it was able to do one, but it wasn't able to do the next one. That indicates probably something's wrong with the next. Okay. Okay, so there's M2, right? It's not even calling into M1 at all. It called into branch, but it seems to have not even hit the first item. Oh my gosh, it's right there. You didn't actually. You gotta take the branch of something. Okay, that's bad. And so then we're getting an infinite sequence. Why? Because we're not ending, I guess. I'm not really sure. Because we're not ending. So if this works, we're only calling into find node with value 2. I don't quite get how it can return an infinite sequence since we're only taking the first. But now that we got no printing in there, let's see what happens. Weird. Maybe we were stuck in some other loop. Alright, let's see if the first looks reasonable. Or let's see if anything looks reasonable. So this is for the first for this is for the first for 1, 2. So you're saying 2 is the node you ended up focused on. That's correct, right? Because you're looking for 2. You got nothing to your left. You got this parent node to your above you. I'm not sure when this gets filled in, but then you got nothing to your right too. That seems rightish. Okay. Whoops. Okay, so if you do this, you end up returning nil. And that's a little surprising. It should return something different than... Oh, it returns the lock, actually. Oh, it returns... Is that the lock that's... You're saying that this is not equal to nil. Okay. Yeah, that is... It should return something, right? But it actually returns nil, which kind of indicates it's C1 and... Oh, well, you do call into this still, so actually it just returns nil. maybe. Let's go slightly more complicated. 1, 2, 3. Let's start at 2 and 3. Actually, let's just invert this one just for the. It should be 3. Oh, there are 2. Yeah. Okay. How about 1, 2, and 3 starting at 2 and 3? Poop. 1, 2, and 3. Node lock. Not equal to 1, 2. Oh, well, yeah, we didn't actually change the thing, did we? Okay. Now let's go deeper. Let's say you start, let's actually start at a common basis. I'm going to have nothing in here, but then I'm going to start at 4. And I'm also going to start at 5 with a child of 6, right? And so I feel like if I start at 6, actually I have it better than this one. What if we start 1, 2, 3, right? Now, that should be the result, but if we start at 2 and 3 respectively, we should actually see, they should end up being 1, 2, actually no, they should end up being 2, 3, right? 2, 3 are the common starts. Okay, that looks okay. Let's do a kind of complicated one. I'm going to start at 6, and I'm also going to start at 4. And what does that mean we should link on? We should link it, I believe, this one, right? Did I screw something up? It looks like. Interesting, okay. So that looks pretty good, I think. Really gotta think about a kind of a better form for so unfortunately I took a little too long on it, but yeah, we gotta think about a better form for just building, you know, if I get a tree problem, I need to have a zipper data structure just standing by that's good. I like this form better, right? It's the zipper is slightly more complicated, but on the other hand, the oh, well, let's chill. Oh, the nils. I forgot about the nils. What about if I start 5, nil, and 6? Now it should be 5. Oops, it's not like that. It's actually 5, nil, and 6. Nobody should have nil for a value. Oh, I'm glad that worked. Okay. But yeah, so I mean, although it's kind of not the correct format for it, what about just 5, nil, where I started 5? Like, that's a weird. Actually, I'm not clear if it'll return. I think it may actually clean this up for us and make it 5. Let's see. Nope, it actually leaves it alone, which that's what I don't like about. That's what I don't like about things that change structure. I mean, it's cool to be able to express it in a more succinct way, right, without the nils if they're not necessary, but at the same time, it means that the thing changes, you know? So I think we have to agree that you can't do this, you know? You have to express it in its minimum form, you know? Because otherwise I can't do equality, right? Because technically it's a different looking thing. So I would stick with that personally. And how can we enforce that? Well, I mean, we could just There's no function that's called every time. Yeah, I don't know how to enforce it. I mean, we could do I guess, a tree walker that just walks through the entire every vector and says, "Hey, you can't have trailing nils," you know. And we could run that before we actually build a zipper, right? Now, of course, that would mean that every time, previously, creating a zipper is an almost free operation, right? It's like you need to create one vector and put the item inside it, put some stuff on the metadata on that vector, and that's it. But if you have to do a tree walker where you confirm that the entire tree is set up in a reasonable way or in the expected way, then yeah, that's bad. Maybe if we could catch it over here, you know. So if I could say like, I mean, that'd be like another cond right here. When I'm getting the children, if I look at them, I prefer not to. Yeah, let's just assume that the tree is passed in a valid form, you know. And okay, that's cool. I was kind of gonna try to. So it's cool for two reasons. One, I actually kind of solved it in close to the 45 minutes I think I'm gonna have to do it, which is pretty good for my batting average right now. But one thing I said I was gonna try to do, yesterday to myself, was maybe see if we could get spec in here, because like this isn't a difficult thing to generate really, and it would be nice to just generate an infinite permutation of these, um, well, a very large number of permutations, and so I'm gonna see if wouldn't it be nice if Babashka had spec in it. I guess we should just give it a shot. Actually, though, I'm not 100% sure. Yeah. Kind of thought maybe I'd seen this here, but maybe I just made that up. I'm curious about this. Add Joki, AWS. Ooh, my neck. Okay, anyway, let's just try bringing in closure.spec. So I think maybe it's just like require closure.spec. I can't remember if the alpha is still there or closure.spec. All right, org.closure.closure. Okay, closure.spec.alpha is spec. Okay. See if it. Oh crap. Well. Hey, where did my Slack? Oh, there it is. Okay. Oh, that's a lot of new messages. All right. is babushka. Holy crap, I'm just trying to paste here. Oh wait, that's right, Ooh, okay. I don't actually, this is embarrassing, but I actually do not know how to copy out of this. Oh, maybe I can just do an actual... See, I used to, I would do this from Windows, but that doesn't exist as a program. What is the equivalent of pbcopy in Linux? Okay. Let's see. So if I select this, and then I do this, then I do this. Alright, let me just try typing it manually. Xclip. Selection. Clipboard. Oh, that didn't work. Alright, try it again. Xclip. Selection. Clipboard. Oh, screw it. I'll just type it. You might... Oh, I guess I need to install Xclip. I'm a genius. But really, there's just no command to use the copy and the paste. I have to install something to have a clipboard. But why is Xclip not installed by default? That seems almost unbelievable. Default Ubuntu clipboard. Oh my gosh, really? Alright, well, whatever. Strange. Require code respect office. I mean, I guess, strictly speaking, Babashka is not a standard version of Clojure. I don't know. I don't know enough about it, but I will ask. And okay, so ignoring that, I guess let's go to the next problem. Well, no, I'll give it a minute or two. And then, uh, all right. I have a suspicion, maybe not, since this is kind of alpha software still, and maybe Babeshka is trying to be more stable for shell scripts. So if that's the case, that's fine. I mean, we have tests here. It'd just be kind of interesting to one time write them as closure spec tests. But I think that's mostly it for 4.8. So I guess yeah, we'll punt on that for now. And yeah, stage this, which all we did was actually make it so that it can compile at the beginning. Stage this, which is the actual problem. Oops, we can take out this print line pass thing. Yep, okay. Oops. Every time. What was that? Open this. Ah, stop helping me. It's annoying. Dude, I'm pressing Control F and you're opening up some stupid action thing. Oh, come on. Okay. You're not helpful. Commit. Boop. 4.8, the practical review. It was first common ancestor.